Hello dear students, welcome to Ezee Notes. Today we're going to start a first chapter, that is force. Class 10 ICSE first chapter, that is what? Force. In that we'll learn the first part today. In that is moment of force and equilibrium. Okay. So basically what is force? So force is something which is known as a push or a pull, right? Force is what? It is a push or a pull. In simple terms, we can say that force is a push or pull. If you have to move any object away from us, we'll push it. Or if you have to move any object towards us, we'll pull it. Simple. That is nothing but force. Anything which changes the state of a body is known as force. So in simple terms, in force applied on a perfectly rigid body only causes motion in it. What happens? See here, this is a rigid body. Okay, I'm applying a force here. I'm applying a force here. So what happened? What happened is there is a motion in this body. It was at rest initially. It is at rest. Now I'm applying the force here. So it is moving. So it is a rigid body, right? So for a rigid body, force causes only motion in it. But when it is applied to a non-rigid body, it causes both change in size and shape and motion as well. Like if you consider a sponge ball, okay. So what happens in that? If you apply force, that means if you squeeze it, what happens? The shape will change, the size will also change, and it can be in also motion, right? If I squeeze and I throw it, what happens? There is a change in size, there is a change in shape, and as well as it is in motion. Okay, so for a rigid body, so force causes only motion, but for a non-rigid body, force causes change in size, change in shape, and motion as well. Okay, next, what is force? Force is numerically termed as it is the rate of change of momentum. What is that? Rate of change of momentum. Okay, so we can write it as force is nothing but dp by dt, where p is momentum. P is what? Momentum. P is momentum. Okay, and the formula for momentum is m into v, mass into velocity. Okay, so what can be the another formula for force? So let us see. So force is nothing but dp by dt, right? So I can write it as d instead of p mv by dt. If mass is constant, if mass is constant, so what happens here? Mass comes outside. What is dv by dt? dv by dt. Rate of change of velocity is nothing but acceleration. So we can term it as force is equal to mass into acceleration. F is equal to ma. When? If mass is constant, then. Okay. And most of the times, the mass of the body will be constant. Okay. Many times. Next, its SI unit is Newton. SI unit of force will be Newton. And commonly used unit is kilogram force. What is the commonly used unit? kgf. Kilogram force, not another kgf. Okay, kgf means kilogram force. Okay, mostly used unit. So 1 Newton, okay, let us say 1 kgf is equal to g Newton. What is g? G is acceleration due to gravity, and acceleration due to gravity, what is the unit of acceleration, value of acceleration due to gravity? That is 9.8 meter per second square. Okay, so 1 kgf is nothing but 9.8 Newton. 1 kgf is how much? 9.8 Newton, or approximately we can say it as 10 Newton. Okay, usually we use 9.8 Newton. Okay, and its CGS unit is dyne. CGS means smaller unit. Okay, CGS unit is how much? Dyne. So 1 dyne, 1 Newton is equal to 10 to the power 5 dyne. It means that compared to dyne, Newton is a very large unit. That is 10 to the power 5 times dyne. Okay, 1 Newton is how much? 10 to the power 5 dyne. And 1 kgf is how much? 1 kgf is 980 dyne. 1 kgf is how much? 980 dyne. Okay, we have to remember this. 1 Newton is how much? 10 to the power 5 dyne, and 1 kgf is 9.8 Newton, and 1 kgf is also 980 dyne in terms of dyne. Okay, so basically force was a what? It was a pull or a push. And if you apply force on a rigid body, there will be only motion. If you apply force on a non-rigid body, there will be change in size, shape, as well as the body will be in motion. Okay. Next, force was what? It was the rate of change of momentum. And if the mass is constant, force can be written as F is equal to ma. And the units are Newton. Commonly used unit is kgf, and CGS unit will be dyne. It is also a vector quantity. It is a vector quantity. What do you mean by vector quantity? Vector is something which has both magnitude as well as direction. Okay, so this force will have magnitude as well as direction. See, if someone hit you, okay, if someone gives you a slap, so what you will say? If your brother or sister hits you, you will go and say to your mom, he or she hit me. Like, she'll ask how. You won't show to your mom. You'll just say this way, that way, right? But because force has a direction as well as magnitude. See, if someone hit me like this, I can show the direction that he has hit me like this, right? The direction. And how hard he has hit me, that is the magnitude. Simple. So force will have both magnitude and direction. That is nothing but a vector quantity. So force is a vector quantity. So next we'll talk about effects of forces. What are the different types of effects due to forces? Force can make a stationary body move. Simple. This is a stationary body. If I apply force, this body is moving. So for example, they have given a door remains stationary until you apply a force by pushing or pulling it, which makes it move. Correct, right? If you have to go somewhere, you have to open the door. You will be standing like this, kulja sim sim. It will open. No, right? So it won't open. You have to pull or push. Okay. At that time, it will open. Next, force can stop a moving body. If a body is moving, see, this body is moving. If I apply the force, it will stop. See, if this body is moving, see, it is going down. If I apply force, it will stop. So force can also stop a body. When? How? If we apply the force, the body will stop. If we apply the force in the opposite to the direction of motion. See, this is going like this. I am applying force from downward. That is nothing but opposite to the direction of motion. So we can stop any object by applying the force. If something is going front, if someone is going front, we can stop them by applying the force towards back. Okay. When a fielder catches a ball, his hands apply force opposite to the motion and the ball comes to rest. See, the ball is coming like this. We are applying the force like this. So we are catching the ball, right? When we catch the ball, what happens? The force applied to the ball will be in the opposite direction of the ball. So the ball comes to rest by balancing the force. Okay. Next, what we can do? Force can change the direction of a moving object. See, this might be going like this. Let us consider a steering wheel. Okay. Normally a handle of anything, bike. Okay. I'm riding a bike. If I have to turn, what I'll do? I'll apply a force on a what? On the handle. I'm applying the force on a handle. What happens? The handle will turn and the direction also will be shifted towards left or right where I'm applying the force. Simple. Here also they have given the same example. When you turn the handle, apply force, the direction of the moving bicycle changes. Moving bicycle, what happens? Changes. Simple. If I apply the force on a steering as well, right? If I apply the force, what happens? The direction also changes. So force can move a stationary object, force can bring any body to rest, and force can also change the direction of a body. Next, what can be done? Force can change the speed of a moving body. How we can change the speed of a moving body? See what happens. If any body is moving, let me consider, if anyone is moving like this, if I go and push them, what happens? The speed will increase, right? Simply what happens? The speed becomes double, triple, whatever. It just simply increases. Okay. Example, by applying force with the oars, the boat already in motion moves faster. What happened? We are applying the force with the oars. Oars is what? Which is used to move the boat, right? The boat is already moving with a constant velocity. If you apply the force by the oars, what happens? The boat will move faster. Or else simple, if I'm riding a bike or car, if I'm riding a bike, what happens? Bike is moving with a constant velocity. If I apply the force, if I apply the accelerator, the acceleration increases. That means that force also increases. So force is applied. So what happens? The speed will increase. Okay. Next one, force can change the shape and size of an object. Simple. For a first example, non-rigid body, right? Force can also change the shape and size of the object. Example, when you squeeze or press a rubber ball with your hands, its shape changes. Okay. Next, types of motion. Next is what? Types of motion. A rigid body, when acted by a force, can have two kinds of motion. One is translation motion or linear motion, and one is rotational motion. Translation or linear both are same, and other one is rotational. So what is translation motion? The first thing, linear or translation motion. Linear translation motion means if I apply force on any object, if it moves in a straight line where it is being placed, okay, it is placed here in the x-axis. If I apply force and it is moving in a straight line, see, it is moving in a straight line, then this motion is said to be a linear or translation motion. Simple. When a force acts on a stationary object which is free to move, the body starts moving in a straight path in the direction of force. Where we are applying the force, in that direction the body will begin to move. So this is called linear or translation motion. Okay. For example, on pushing a ball lying on the floor, it begins to move in the direction of the push. See, this is an object. Instead of ball, we can write it as object. If you push an object by applying the force, the object, what happens? It will move in the direction of force in a straight line. That is known as translation motion. So, next thing, what is rotational motion? See here, see. This is like this. If I apply force upward, it will go upward. If I apply force downward, it will come downward. This is linear or translation motion, right? If I apply force here, what is happening here? The object is being rotated. The object is being what? Rotated. See, the object is rotating like this, right? It is rotating, but we can see that there is a single axis about which it is rotating. There is an axis about which it is rotating here. This axis is known as axis of rotation, or we can say it as pivoted point. Okay, see, if a body is pivoted at a point and the force is applied on the suitable point, the body is pivoted here and the force is applied to any suitable point, it rotates the body about the axis passing through the pivoted point. This was a pivoted point, the axis was passing from here, I am applying the force here. So this body comes in motion, and this type of motion is known as rotational motion. This is the turning effect of the force. There is a turning effect of the force. The force gets turned like this, right? Turning effect of the force. So this turning effect is known as rotational motion. Okay. See, this is the axis, that is pivoted point of a door. If I apply the force here, the door comes in, goes out like this, right? We can pull or push the door. So what happens about this point? About, see, the best example is my joint. Okay, this is a pivoted point. I can move here and here. This is rotation, right? This is rotation, or this is rotation. See here, this is a pivoted point. About this axis, what happens? There is a force applied. So this is nothing but a rotation. Simple, yeah. So for example, when a force is applied normally on the handle of the door, normally means perpendicular. Normally means what? Perpendicular. How will apply the force on the, see, I am applying the force like this, not like this. See here, consider this. If I apply the force like this, normally it will move, right? If I'm applying the force like this, is it moving in rotation motion? No, right? We have to apply normally. That means perpendicular. See, perpendicular to the surface. Okay, or perpendicular to the point of pivot. Next, the door begins to rotate about an axis passing through the hinges on which door rests. About that point, the door was resting. If I apply the force at a suitable point, the door begins to move or it begins to rotate. That motion is known as rotational motion. For example, if a wheel is pivoted at its center, it begins to move if I apply the force on the rim. A force is applied tangentially on its rim, the wheel rotates about its center. So this motion is known as rotational motion. Two kinds of motion, right? Linear and rotational, or translation and rotational. Next thing, moment of force. What is moment of force? It is also known as torque. Okay, moment of force or torque. The turning effect on a body about axis due to moment of force applied on the body. This turning effect is due to what? It is due to moment of force. It is due to torque. If the body has torque, it will rotate. If the body don't have torque, it will not rotate. Simple terms. If the body is having what? Torque, it will rotate. If the body is not having torque, it will not rotate. So the moment of force is equal to product of force and perpendicular distance. force and perpendicular distance. See, if this is the pivoted point, okay, if I apply the force like this, F, and this is distance R, so now the torque will be, torque is nothing but we denote it as tau, okay, it is known as tau, a small t, t type, a bended t, we can say. Tau is equal to R into F. F perpendicular. Both should be what? Perpendicular. Remember, both should be perpendicular. What happens if I apply force at some angle? See, this is the pivoted point. I am applying the force like this at some angle theta. Okay. Now, what happens? This force is being acted like this, right? Now, this force will have two directions. Any vector will be having two directions. See, I'm here standing. Okay. If I apply force right side, I'll go right side. If I apply force left side, I'll go left side. If I apply force upward, I'll go upward. Right? If I be applying force like this, I'm going up as well as front. Right? See this. It is going like this. It is going like this. If it goes like this, it's also going front as well as upside. What happens? What is happening here? The force is being applied in both the axes, right? So some part of the force will be in the x-axis, Fx we can say, and some part of the force will be in y-axis, Fy we can say. Okay? Okay. So now here, if we resolve the component of forces, the x component, yani the component which is along theta, that will be a cos component, F cos theta. Along theta will be cos component, and across theta will be sine component. So we can say it as F sine theta. Okay. If I had taken theta from here, this would be F cos theta and this would be F sine theta. Remember that, okay? So along component it will be F cos theta and across component it will be F sine theta. Now tell me, which force is responsible for rotating an object? This is R, for rotating. Now we have resolved this F, so there is no F now. There are two components of F, Fx and Fy. Okay. Now which is responsible for rotating the object? See, there is a spanner here. Okay. I have to loose the nut. What I'll do, I'll apply the force like this. Right. See, this is the pivoted point. Fx is this. Fx is this. I'm applying the force here. Will it rotate the object? No, it's not rotating. So this is not responsible for rotation. It is not responsible for rotation. If I apply the force like this, see that? There is a rotation, right? If I apply the force perpendicularly, there will be a rotation. So this is responsible for rotation. So here now I can write as torque is equal to distance into perpendicular force. Anything, either perpendicular distance or perpendicular force. Both should be perpendicular to the symbol. So I can write it as tau is equal to R into which F will take this perpendicular F, which is responsible for rotation. R into F sine theta. If there is an angle, we can take this. Okay. This is an extra knowledge. Okay. Now, what is if theta is equal to 0 degree? This is that thing, right? If theta is 0 degree, yeah. If theta is 0 degree, what happens? Sine 0 is 0. So therefore torque becomes 0. So that's why due to Fx there is no rotation because there is no torque. Understood? Yeah. What happens if theta is equal to 90 degree? Sine 90 degree is 1. Sine 90 is how much? 1. So torque will be maximum. That is R into F. Torque will be what? Maximum. That is nothing but if we apply the force perpendicularly, the rotation will be maximum compared to if I apply the force like this. Because while applying the force perpendicularly, the total force will be acting towards perpendicularly, right? But if I apply the force at some angle, some of the force will go in the x-axis as well as some of the force will go in the y-axis. So the y-axis component here, in this example, the y-axis component is helping to rotate the body, right? So it is what we can say? We can say that if you apply the force at some angle, the force will be not maximum, there will be something force, there will be some torque. Okay, if I apply the force at 0 degrees, that is nothing but parallel to the direction of pivoted point, the force will, the torque will be 0. There is no rotation in the body. If I apply the force perpendicularly, the torque will be maximum. Remember that. Done. Easy. So, next, what is the SI unit of moment of force? See, force is moment. The unit of force is Newton, and the distance unit is meter. So the SI unit will be Newton meter. Okay, and the CGS unit will be dyne centimeter. Dyne centimeter, because CGS unit of force was dyne, and CGS unit of distance will be centimeter. So the CGS unit of torque will be dyne centimeter. Next, PYQs. Rotational motion in a body is related to turning effect in a body. True. Application of force on a pivoted point. Yeah, both A and B are correct. Right. For both of them, it will relate. Next, the moment of force about a given axis depends on what? On all it depends. Torque will be equal to force into perpendicular distance. The turning effect in a body only on the magnitude of force? No. Not only on force. Only on the perpendicular distance? No. Neither on force nor on both on force and its perpendicular distance. This will be the answer. Easy? Yeah, not easy. Next, why is it easier to push a door at its free end? See what happens. This is the pivoted point. Okay, here it is hinged. Why is it easy to push a door at its free end, not here? See what happens. Torque is equal to distance into force, right? Now, there will be some torque required to open or close a door, right? And torque will be constant. There will be a constant torque required, right? That is simple thing. To rotate this body, there will be a constant torque required to rotate this body. For any body to rotate, there will be a constant torque. Okay. So there is some constant torque. If I apply the force here, the distance is this. So there might be some torque tau 1. Okay. So here R into F, if I do R1 into F1. If I apply force here, there will be distance this. That is nothing but tau 2 R2 into F2. But here tau 1 and tau 2 should be same, will be same actually, because the torque required is same to open or close a door. Here, see here, this is R1, this is R2, right? R1 is less than R2. R1 is what? Less than R2. So for torque to be remembered, F1 should be greater than F2, right? F1 should be greater than F2. So if I apply force here, see, for live example, if I apply force here, same force, it is rotating, right? If I apply force here, see, it is taking time to rotate. Because at smaller distance, we need larger force to balance the torque. At larger distance, we need smaller force to balance the torque. So why is it easier to push a door at its free end? Because at larger distance, we require a minimum force to rotate a body or door. Done? You can write it down. Go back 10 seconds ago, I'll be telling you the answer. Okay. Next, a door lock is opened by turning lever. Handle of length 0.2 meter. Handle of length how much? 0.2 meter. That is nothing but R is how much? 0.2 meter. If the moment of force produced is 1 Newton meter, how much is moment of force? 1 Newton meter. Then the minimum force required is, what is the force? Simple. So what is the formula for torque? Torque is equal to force into perpendicular distance. So what will be the force here? Torque by perpendicular distance. So how much is torque? Torque is 1 by perpendicular distance is 0.2. So 0.2 into 5 times will be 1. So the minimum force required is how much? 5 Newton. Easy. Next, the moment of force of 5 Newton about point P is 2 Newton meter. They have given force how much? 5 Newton force. So for that, the torque produces 2 Newton meter. Calculate the distance of a point of application of the force from point P. Now we need to calculate the distance R. So can you calculate this? Tau is equal to R into F. Yeah, so F into R, anything is fine. FR. So R will be equal to tau by F. So comment this answer. Okay. What will be the answer? Next. A mechanic can open a nut by applying a force of 150 Newton. How much force? 150 Newton. While using a lever handle of length 40 centimeter. How much? 40 centimeter. What length of handle is required if he wants to open it by applying a force of only 50 Newton? Okay, see here. Initially, he was applying at 40 centimeters, so he required 150 Newton. He might be applying at some distance, so he'll require only 50 Newton to open the door, open this nut. So this is F1, this is R1. So F2 is how much they have given? 50 Newton. So what will be R2 they are asking? Simple. We know that at this point torque will be same. Tau 1 is equal to tau 2 because to open anything the torque remains constant. So tau is what? F1 R1 is equal to tau 2 will be F2 R2. So what is F1? F1 is 150 into R1 is 40. F2 is 50 into R2. So 50 ones are 50, 50 threes are 150. Right? So 3 into 40 is 120. So R2 is how much? 120 centimeter. R2 is what? 120 centimeter. To convert centimeter to meter, we have to divide by 100. So R2 will be 120 by 100 meter. So 120 by 100 is how much? That is 1.2 meter. Easy, easy, breezy. So we'll move to next question. A spanner of length 25 centimeter. How much? 25 centimeter is used to open a nut. To produce a maximum turning effect. How much? Maximum. Force should be applied. Simple, at 90 degrees. This wasn't required. They can simply ask to produce a maximum turning effect. Where must be the force applied? That should be perpendicular to the distance, that is at 90 degrees. I have explained you. So let's go to the next topic. That is clockwise and anti-clockwise movements. So conventionally, if the effect on the body is to turn anti-clockwise, to turn what? Anti-clockwise, anti-clockwise, anti-clockwise. The moment of force is called anti-clockwise movement. We call it as anti-clockwise movement, and it is taken to be positive because antis are always positive. But uncle will be negative, right? Yeah. So see here, anti-clockwise, anti will be positive. Opposite of anti, uncle. No, here it is clockwise. Anti-clockwise opposite will be clockwise. So clockwise will be negative. Simple. So anti-clockwise movements are considered to be positive, and clockwise movements are considered to be negative. Simple. So here, clockwise are considered to be negative. And the moment of force is also a vector quantity. The direction of anti-clockwise movement is along the axis of rotation outward. See here. If I turn my hand like this, anti-clockwise, where is my thumb pointing? Outward, right? So this will be the direction of moment of force. That is nothing but torque. Torque will be where? Outside. See, that's why if I open any bottle like this, anti-clockwise, it will get loosed, right? Let me find a bottle here. Just a minute. See here, there is a bottle here. If I apply force anti-clockwise, the force will be upward, right? Anti-clockwise like this, the force will be upward. If I apply clockwise, it will get tightened. This bottle is not of clockwise or anti-clockwise. It is normally push and pull type of force. Any object you can try with your own water bottle. If you want to open, you will rotate it like this in anti-clockwise direction, because if we rotate in anti-clockwise direction, the torque will be acting upward, so the bottle will get opened. To close, we will apply it on the clockwise, so it will get downward. See, downward, moment of force will be downward, so it will get closed. Okay. Next, the direction of rotation of a body can be changed in two ways. How can we change the direction of rotation? If it is rotating like this, how we can change like this? Okay, by changing the point of application of force. See here, I am applying the force here. If I apply the force here, the direction will be changed. See, I am applying the force here. If I apply the force here, the direction of rotation is changed. By changing the direction of force itself. See, I am applying force from downward to upward like this. From downward to upward like this. the point was changed, right? So first thing is proved. Second thing, I'm applying force upward, I'm applying force downward. If I apply the force upward, it will move anti-clockwise. If I apply the force downward, it will move clockwise. Simple. Chalo. Both are done. Next, let me go for PYQs. Figure shows. Where is the figure, man? We'll draw. Figure shows a uniform meter rule weighing 100 GF pivoted at its center. Okay. Its weight is how much? 100 GF weight. And here it is pivoted. For pivoted, it is, I'll put like this. Okay. Two weights, 150 GF and 250 GF, hang from meter rod as shown in the figure. Where is the figure, man? Just a minute. I'll get the figure. We got to know the figure. The figure is like this. From here it is 40 centimeter and the force acting is 150 GF, and from here for 20 centimeter 200 GF, 250 GF is acting. Okay. Calculate the total anti-clockwise moments about. First thing, listen carefully. Any force which is acting along the pivoted point, it does not produce any torque. See here, it is like this. If I apply force here, like this, see, at the pivoted point, is this rotating? No. So, due to its own weight, there will be no torque. That is no moment of force. Now, the moment of force will be due to this and this. So, how we will consider if it is producing anti-clockwise or clockwise moment? First, from pivoted point, keep your hand. Okay, keep your hand like this, right hand like this, anyway. I'm keeping like this. Okay, and curl your fingers towards the direction of force. See here, for 250 GF, this is the pivoted point, I will keep like this, and 250 GF is downward. So what will be the moment? Which direction it is going? Clockwise. This is going like this, clockwise. Due to this, the torque will be clockwise. And see here, this is pivoted point and 150 is acting downward like this. That means like this. Due to 150 it is going anti-clockwise. So simple, we can solve. So total anti-clockwise is due to 150 GF. We can read as the sorry, the anti-clockwise tau is due to 150 GF. So what will be anti-clockwise torque now? That is distance into force. So anti-clockwise torque is equal to, how much is the distance from pivoted point? See here, that is 40 centimeter. 40 into the force is 150. 40 into 150. So what is 40 into 150? 15 fours are 60. That is nothing but 6000 GF centimeter. This will be torque, anti-clockwise torque. Okay. Now, next is the total clockwise moment. Clockwise is due to 250. 20 into 250, simple. Can I move this here? Let us see. Yeah, I can move this here. A array. This is A. No, B is what? Here I'll do B. Total clockwise. Clockwise torque is due to 250. So R into F. So clockwise torque is R is 20 into 250. That is how much? 5000 GF centimeter. This is clockwise torque. Done. Okay, done. Now next, what they are asking? The difference of anti-clockwise and clockwise movement. Difference, simple. See, delta tau is equal to tau anti-clockwise minus tau clockwise. Anti minus clock, because this is more, this is a simple. So delta tau will be equal to 6000 GF centimeter minus 5000 GF centimeter. So delta tau will be equal to 6000 minus 5000, that will be 1000 GF centimeter. and 1000 GF centimeter is acting where? Anti-clockwise. Remember that extra 1000 is where? Anti-clockwise. Okay. Chalo. Next we'll see the distance from O where 100 GF weight should be placed to balance the meter rule. Now what happens? The total torque is like this. That means that the meter rule is not straight. It is going like this because anti-clockwise force is more, torque is more, right? So it is going like this. So to balance this, where I have to place the 100 GF weight? For sure, from pivoted point, I should place at the right side so that if it balance like this, the meter scale will be straight. This is nothing but it will be balanced. So I should place first thing we need, right? To balance the extra 1000 GF centimeter ACW torque, we should place 100 GF at on the right side, 100 GF on the right side of pivoted point at x distance. At x distance, that x will calculate. Okay, where we are. See, from here, let us consider at some x distance. Here, 100 GF. Any x distance, it can be here as well, or it can be here. Anything is fine. I'm just putting at some x distance. Okay. So what will be the extra torque? Delta tau is nothing but 100 GF into x centimeter. So delta tau is how much? 1000 is equal to 100. This is 1000 GF centimeter, right? Simply I'll write 100 to x. 100 into x. So 100 into x. So 100 tens are 1000. So x will be how much? 10 centimeter. So we must place at 10 centimeter from the pivoted point to balance the meter scale. Simple. Where we should place the 100 GF. See, where we should apply the 100 GF weight to balance at 10 centimeter from somewhere here. Okay. Easy. Chalo. Next, a moment of couple has a tendency to rotate a body in anti-clockwise direction. Anti is always positive. The moment of couple is taken as positive. Simple. What is couple? We'll study in just few minutes. A, B, and C are the three forces, each of magnitude 4 Newton. See, three forces: A, B, as well as C. All are of 4 Newton. 4, 4, 4. As shown in the figure, the point O lies in the same plane. Okay. Which force has least moment about O? Give reason. See, what is torque? Moment of force. That is nothing but moment. Moment is nothing but torque. Tau is nothing but R into F. No. F is same for everyone. F is same. So tau is directly proportional to R. It means that greater the R, greater will be moment. Lesser the R, lesser will be the moment. Simple. Okay. He's asking least moment. Least moment will be due to, this is 0.9, 0.8 and 0.6. That will be due to C. I can write it simple. The least moment will be due to C. And how much it will be? Tau is equal to 0.6 into 4. That is nothing but 2.4 Newton meter. Simple. Least moment will be due to C. Which force has greatest moment about O? Greatest moment will be due to A, right? Because it is 0.8, 0.6 and 0.9. Greater the distance, greater will be the moment. So how much it will be? Tau is equal to R into F. So you can do how much it will come. You can say that. Okay. Next, name the forces producing clockwise and anti-clockwise moment. Now it's time for this right hand. So what we have to do? We have to keep the hand like this from pivoted points. First we'll solve for A. It's like this and it's going upward. That means that in this direction. Chalo. See, this is the direction of A. That is nothing but clockwise. A is clockwise. So again here I am keeping, this is B. Okay, this is also clockwise. For C I'll keep like this, and this is C. It will be anti-clockwise. Done. So now which are the clockwise? A and B. And which is anti-clockwise? Only C. Okay. What is the resultant torque about point O? Resultant will be simple. Tau resultant will be tau A plus tau B plus tau C. So tau C we got here. Array, this has been erased. It was 0.6 into 4, right? So it will be 2.4 Newton meter. See, tau C we have got 2.4, and tau A will get from here 0.9 into 4 is 3.6, and tau B will get from here, it will be 0.8 into 4, 8 for 32, 3.2 Newton meter. So simply we have to add them. 3.6 plus 3.2 will be 6.8, 6.8 plus 2.4, 9.2, I think. 9.2 Newton meter. That will be the answer. Simply we have to add them. No, this is wrong. We don't simply have to add them. What we'll have to do? See, for clockwise, negative. So minus 3.6 and minus 3.2. And for anti-clockwise, it is positive. That is plus 2.4. So if I calculate this, it will be tau is equal to minus 3.6 minus 3.2 will be minus 6.8. Minus 6.8 plus 2.4, that will be minus 4.4 Newton meter. So we can say it as net torque is 4.4 clockwise. 4.4 Newton meter clockwise. Minus means clockwise, right? Yeah, simple. Next is couple. What is couple? You and she. No. Couple is something which is required to produce a pure rotation. See, this is the object like this. If I apply force here downward and here upward, see, same amount of force upward and downward in the same line of action. So it will produce a pure rotation. See here, see. I am applying a force F like this and F like this. Same force I am applying. For a pivoted body, a single applied force along with the reaction force at the point forms a couple that rotates the body. For single application of force, there will be another opposite reaction force. It produces a pure rotation motion like this. See here? Like this simple. See, I am taking this downwards and this upward. See, like this. This is pure rotational motion. Equal and opposite forces reacting on the same line of action produces a couple. Equal and opposite forces reacting on the same line of action produces what? Couple. See, the distance between them is d. If the distance between them is d, so moment of couple will be either of the force into distance between forces. Okay, that is nothing but moment of couple. This is the formula for moment of couple. That is nothing but tau of couple will be equal to force F into distance between them is d. The distance for both of them between those two forces. Here net force will be 0 because it is acting upward, it is acting downward. But net moment of force is not 0. If net force is 0, that's nothing but there is no translation motion. If net force will be 0, there is no translation motion. If net torque is 0, there will be no rotation. But here net force is 0 means there is no translation, but net torque is not 0 means there is only pure rotation. That is nothing but steering. If I rotate the steering, see here, I am applying the force here this way. I am applying force here downward and here upward. So this is rotating steering. And for the tap, if I apply force like this, see, this is like this, this is like this. So it is getting rotated, right? So this is nothing but couple. Sure, we'll come for few examples. Question: the resultant moment of couple, if two equal forces of 6 Newton, how much of force? 6 Newton are acting at a distance of 3 centimeter each from the center. From center, see here, this center 3 centimeter, and from here 3 centimeter. It is asking like this, it is acting like this. So total distance will be 3 plus 3, 6 centimeter. This you need to remember. The distance should be between two forces, not from center. Okay. So what will be the resultant moment of couple? Tau is equal to R into F, simple, or F into R, simple, 6 into 6. It is nothing but 36 centimeter, Newton centimeter. Newton centimeter. But they have asked in Newton meter. So change it to Newton meter. First we'll change D from 6 centimeter to meter. So divide by 100. So it will be CD is equal to 6 by 100 meter. That is nothing but 0.06 meter. So we'll multiply here F into D. So F is 6, it is 0.06. 6 6 is 36, it will be 0.36 Newton meter. How much will be torque? 0.36 Newton meter. You can easily calculate them. Easy? So, next question. If the handle of the door is connected at the middle of the door, here, this is the handle. The turning effect on the door will be very large, not very large. See, very large will be when if I place the handle here at the point of contact, that is nothing but at the hinge point, there will be too much force required to open the door like this here. Too much force is required. Okay, it's not. Less force is needed to produce greater turning effect. No, less force is needed when we apply the handle here. So here less force is required. This is also not the answer. Next, all of the above will not be the answer because these two are wrong. More force is needed to produce a greater turning effect. Yeah, at middle, more force is required. So this is the answer. Next, a body is acted upon by two unequal forces in opposite direction. Forces are not equal. That means net force is not equal to 0. But in opposite direction. Opposite direction means net torque is also not equal to 0, but not in the same line. This effect is, the body will have only rotation? No. Only rotation means the forces should be equal. That is, net force should be 0. The body will have only translation? No. For that, net torque should be 0. Okay. The body will have neither rotation nor translation? No. For that, both should be 0. The body will have rotation as well as translation. Yeah, for this, both should be non-zero. As the both are non-zero, the answer will be the body will have translation as well as rotational motion. Okay. Next, equilibrium of bodies. The same thing which we learned now. Equilibrium of bodies means when a number of forces acting on a body produce no change instead of rest or linear or rotational motion, then the body is said to be in equilibrium. That means that net force should also be 0 and net torque should also be 0. At that time, the body will be in equilibrium. Okay. See, now there is no force acting here. See, there are two types of equilibrium as well. See, condition for equilibrium, the resultant force should be 0 and the resultant moment of force should also be 0. Both things I have said here. And there are two kinds of equilibrium. That is static and dynamic equilibrium. What is static and dynamic equilibrium? Let's example. See, the equilibrium is of two kinds, static and dynamic. When a body remains in the state of rest under the influence of several forces, the body is in static equilibrium. What does that mean? See, this body is at rest. If I apply force like this, any body, let us consider a sponge ball. Okay, I have taken like this and I am squeezing it. It is at rest, it is not moving. I am applying force from everywhere, right? But this body is not moving. So this is nothing but a static equilibrium. Simple. Or a book is lying on the table. Let us example, a pen is lying on the hand. Because the gravity pulls the book down, the gravity is pulling this pen down. The table pushes up with an equal normal force. This hand will apply the equal force so that it is balanced here. If the force applied due to gravity on the pen was more, my hand would go down. Or if the force applied by my hand on this pen would be more than the gravitational force, the pen would go up like this. So to balance each other, there will be equal forces, downward and upward. Forces are acting, right? Forces are acting, but then too the body is not moving. This type of equilibrium is known as static equilibrium. Example is here. Okay. What is dynamic equilibrium? When a body remains in the same state of motion, translation, or rotation. See, you might have seen um, anything moving. Okay. If anything is moving, how will it stop? There should be some force required, right, to stop it. Right? Yeah. What is the force required? Why is the force required? Because if there is no force, the body won't stop. The body, see, the body has a property known as inertia. Okay. Any body will have a property known as inertia. So body wants to remain in the same state. If it is in a state of rest, it wants to be in the state of rest. If it is moving, it wants to be in the state of motion. Either it's moving rotational or translation, anything is fine. If it is in motion, it wants to be in the motion itself. Even though several forces are acting, it remains in the same state. At that time, the body is said to be in the dynamic equilibrium. For example, a raindrop reaches the Earth's surface with a constant velocity. The weight of the falling drop is balanced by the sum of buoyant force and the net force of friction. See what happens? The raindrop will fall at the same speed, right? All the raindrops. See, it's not like for me the rain is coming with high velocity. For someone else, the rain is coming with low velocity. Will that happen? No, right? Every raindrop will have constant velocity. It's moving with constant velocity. Even though many forces are acting, even though weight is acting, upward buoyant force is acting, air friction is acting, many forces are acting, the body is in same. The body is moving with same velocity. Right? At that time, the body will be in dynamic equilibrium. Or an aeroplane moves at a constant height when upward lift and it's balance its weight downward. What happens? When aeroplane is moving upward, there will be a constant force applied upwards to move it. If it is moving upward, it should also balance the downward force. So the both forces will get balanced, even though the plane will be moving. How will be the plane moving? Due to dynamic equilibrium. Okay, the example is of dynamic equilibrium. The weight of the plane will be balanced by the upward force required for lifting of the plane. So, next, we'll go with some questions. A body is said to be under equilibrium if many forces act on a body at a point to produce large state of produce change in state of rest or motion. No, there is no change in state of rest or motion. Many forces act on a body to produce no change in state of rest. Many forces act on a body to produce no change in state of motion. Yeah, there should be no change in state of rest as well as motion. If a body is in state of rest, it should be in the state of rest. If a body is in state of motion, it should be in the state of motion. There should be no change in the state of a body. At that time, the body is said to be in equilibrium. Both B and C are correct. Next, motion of a satellite around the planet is a condition of dynamic equilibrium. Remember, why? Because motion of the planet is around the sun is due to which forces? Due to gravitational force, right? Gravitational force of attraction, and the planet has some weight, so that gravitational force will help the object to be in a simple rotation motion. With constant velocity, it will be moving like this, right? So it won't change its constant speed it will be moving, not constant velocity, because velocity has direction, it will be changing continuously, but speed will be constant. So it will be rotating with an equal speed in rotations, orbits around the sun. So at that time, satellite around the planet, simple like this, it will be rotating. So the force will be balanced. Is which condition? The condition is known as dynamic equilibrium. Simple. Okay. Next. Assertion: stone moving in a circular path showing uniform speed is under dynamic equilibrium. If the stone is moving, is that in dynamic equilibrium? How? See, we can say according to question before here, right? If the satellite moving around the planet is under dynamic equilibrium, why does a stone is not under dynamic equilibrium, or it is under the dynamic equilibrium? Actually, it is false. Okay. So why is it not under the dynamic equilibrium? See what happens. The stone is tied to let us consider I'm tying a stone to a thread. Okay, and I'm rotating it like this. So what happens is, if I increase the speed, the stone might go away from me. That means that the thread will break and stone might go away. It means that there is no fixed force, balanced force. There is no balanced force. We have to balance it. External force is required to keep it balanced. But under this example, there is no external force required to balance. So that's why this is under dynamic equilibrium. Here there is external force required, so it is not under dynamic equilibrium, right? That forces will be balanced, tension and centrifugal force will be balanced, but we are providing some extra force, right, to keep it rotating. That is not balanced, right? So it is not under dynamic equilibrium. A body under uniform circular motion shows dynamic equilibrium because it shows uniform velocity. No, velocity is not uniform. See, if it is rotating like this, sometimes velocity direction will be this. If it's here, the velocity direction will be here. So the velocity direction will be changing. There is no uniform velocity. It is only it only shows only uniform speed. Okay. So both assertion and reason are false. Option D is the right answer. Next, principle of moments. What is the principle of moments? According to the principle of moments, if the algebraic sum of all the forces acting on the body about an axis is 0, that means that for a body to be in equilibrium, see, simple, we don't have to understand it. See, what we did in this question, let me explain you an example. What we did in this question, we had to balance the body, right? We had to balance the meter rule. So there was some clockwise movement and there was some anti-clockwise movement. Anti-clockwise movement was more. So to balance it, what we did, we included some clockwise movement. Simple thing it is saying, for a body to be in equilibrium, according to principle of moment, the total anti-clockwise movement should be equal to clockwise movement. If both are same, there will be no torque. That means that there will be no rotation. The body will remain in equilibrium. Easy? Easy. Chalo. We'll go with some PYQs. A uniform meter rule of mass 100 gram. There is a meter rule whose mass is 100 gram. Okay. Is balanced on a fulcrum of 40 centimeter. Okay. Here there is a fulcrum which is at 40 centimeter mark. So at 50 centimeter mark, we can apply the weight, right? It is how much? 100 gram means 100 GF. Okay, 100 GF force I can apply here. Okay, at 50 centimeter mark. At 50 centimeter mark. Suspended by unknown mass at 20 centimeter. There is unknown mass here at 20 centimeter. There is an unknown mass M here. It is suspended. So here there will be how much force? M into G force. Mg will be acting here. Okay. Find the value of M. Simple. Find the value of M. Force is nothing but mass into acceleration, right? Here the acceleration will be acceleration due to gravity. Now, this is the pivoted point. That is nothing but fulcrum is here. Now, this weight will produce clockwise movement, and this mass will produce anti-clockwise movement. So total clockwise movement is equal to total anti-clockwise movement. To balance this, simple. To balance, it is balanced. To balance this, total clockwise will be equal to total anti-clockwise. So what is the formula for moment of force? Force into distance. Distance from pivoted point. Clockwise is this. 100 into, from here to here distance is 10 centimeter. So 100 into 10 is equal to, from here to here distance is 20 centimeter. So mg into 20. Mg into 20. Right. It is 100 GF, right? So we can write it as 100 G into 10. Because GG will get cancelled again for both of them. From now here, we have to calculate M is equal to 100 into 10 will be 1000 divided by 20. So 0 will get cancelled. So 2 into 50 will be 100. So M is equal to 50 grams. Mass will be how much? 50 grams. Easy. Clockwise is equal to anti-clockwise. Done. Simple. Next. A uniform meter rod is balanced at 70 centimeter. Okay, there is a meter rod here. It is balanced at 70 centimeter. Okay. Somewhere here. Okay, it is balanced there. I'm applying the fulcrum. So this is the provided point. Suspending a weight of 50 GF at 40 centimeter mark. At 40 centimeter mark, there is a weight of 50 GF. How much GF? 50 GF. Okay. And 200 GF at the 95 centimeter mark. At 95 centimeter mark, there is 200 GF force act. Okay. Draw the diagram of the arrangement and calculate the weight of the meter rod. This is the arrangement. And at 50 centimeter, the weight of the meter scale will be acting, W. And we need to calculate this weight itself, the weight of the meter rod. Simple. So first thing, which will produce clockwise and which will produce anti-clockwise. I am keeping like this. This will produce clockwise. This is producing clockwise. I am keeping like this. These both will produce anti-clockwise. 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 Now, from here to here distance is 20 centimeter. Here to here it is 25 centimeter. Here till here. Right, from provided point we have to take, right? Here till here it is 70 to 40, that is 30 centimeter. Right? Simple, we have to do total clockwise movement is equal to total anti-clockwise movement. So clockwise only this. So 200 into 25. 200 into 25 is equal to 50 into 30 plus W into 20. 50 into 30 plus W into 20. Okay. 200 into 25, 25 twos are 50. This 5000 is equal. 50 into 30, 1500 plus 20W. If this 1500 goes here, it will be 5000 minus 1500 is equal to 20W. So 5000 minus 1500, 1500, that will be 3500 is equal to 20W. So W is equal to 3500 divided by 20. 0, 0 gets cancelled. 2 into 175 will be 350. So W will be equal to 175 GF. How much is the weight of the meter ruler? 175 GF. How much is the weight? 175 GF. Easy? Clockwise is equal to anti-clockwise. You got to know how to draw the diagram. Next, last question of the day. On a seesaw, there is a seesaw. Two children of mass 30 kg and 50 kg are sitting on the one side of it at a distance 2 meter and 2.5 meter. This is the fulcrum, right? Fulcrum will be at center. At 2 meter and 2.5 meter. There are two children sitting. Here one. Here one. Of how much mass? Let me change the color. Of how much mass? 30 and 50. 30 is sitting at 2, 50 is sitting at 2.5. 30 GF, right? And here the weight will be acting 50 GF. Okay. Next, from its middle, where should a man of mass 74 kg sit to balance it? It's obvious man should sit here. Okay. Let us consider at some x distance. It is 74 kg. So here he'll apply 74 GF. So after first thing, on the same side will be the wrong answer. On the other side, any one of this will be the answer. We need to calculate x. Total clockwise movement is equal to total anti-clockwise movement. Simple. From that time we are doing this will produce clockwise, and this both will produce anti-clockwise. Sorry, anti-clockwise. Done. So clockwise is 74 into x is equal to anti-clockwise is 30 into 2 plus 50 into 2.5. Right? Okay. So 74x is equal to 30 into 2 is how much? 60 plus 50 into 2.5, 125. 25 5 is 125. Yeah, 125. So 74x is equal to 60 plus 74 kg, right? Yeah. 125 plus 60 is it? That is nothing but 185. Right? 1 minute. Yeah, sorry. So x will be equal to 185 divided by 74. So solve it. 7 2s are 14, 7 3s are 21, right? So it can't be 3.5. It will be 2.5 itself. Simple. Done. Chalo. So by this, the first part of the chapter 1, that is moment of force and equilibrium, is completed. So we'll meet in the next chapter, and sorry, next part of this chapter. Till that time, keep supporting us and follow us. Bye bye.